wasn't. Okay, that's kind of the idea there. All right. Okay, so that's the problem. The hypotheses are as such. The null hypothesis, and again, we don't have any parameters here. Right? There is no mu, there's no p. All right, there is no statistic really that we're really doing, using as an estimate kind of. So in this situation, the hypotheses can be stated in words. The first way, there's many ways in which you can write this, but the gist of what the null hypothesis, what it should say, is that the distribution of the population fits a specific distribution of proportions in each category. So that's like saying, I assume that if there's 4 classes in the population, I assume that it's equally distributed, 25, 25, 25, 25. That's what I could assume under the null hypothesis. Okay, so saying that each class is equal, that is a specified distribution. Okay, 25 across the board. Okay, the alternative would say this: at least one of these proportions is not specified under the null. So what does that mean? What happens under the null, going back to my example, what if I assume that the 4 classes were equal, 1/4 across the board? But then my data tells me that, oh, it's actually 1/2, 1/4, 1/4. Oh no, that doesn't work, sorry. Oh yeah, that doesn't work, sorry. 1/4, 1/3, 1/4, 1/6. What happens if my sample data gives me that distribution? Well, notice that the null is saying that, oh, these 2 matched up, but then the other 2 didn't. So what does this alternative hypothesis say right here? It says at least one of these proportions is not specified under the null. I say at least one because once one is not the same, then that ultimately must make another one different as well, right? So in this case, 1/4, 1/4, those are fine, but because this one's 1/3, this one's actually bigger than that, then that means this one must be smaller than this one, right? Because they should all add up to 1 in this case, all right? So the alternative is just saying, yeah, there's something that's not in the right place, okay? One of these proportions that I had under the null is not right, but ultimately, if one is not right, then that means at least another one must be wrong too, okay? That's what the hypotheses are like, okay? We assume that under the null, it fits that specified distribution. The alternative is just saying, hey, can we find evidence that at least one of these is not right? Because if we can prove that if one of them's not right, then the null is in trouble, yes?
So you don't have to say specifically what's not right, right?
No. No, because as you're gonna see, we're still gonna be doing p-values and stuff. So in this case, once we look at the data, we're gonna say, oh, the p-value is less than 5%, therefore we reject the null in favor of the alternative, but we don't have to specify exactly which one was not in line with the null. Yeah, okay. So we're still just doing the same thing, like making a decision based on p-values and alpha, okay? Any other questions? Okay. So, your guys' favorite. Under the null, so again, exactly what are we assuming when we say that the null distribution for the population is assumed to be true? So, because we're only talking about one categorical variable, just like, hey, what are these classes, right? Is it your high school class? Is it the type of car you have? I don't know. Like, it's just some sort of classification of some sort. So we're going to use a one-way table. When we get to Monday, we're going to do two-way tables. So we're going to be talking about two categorical variables. But for our purposes today, just to ease you into, we're only talking about one. So we're only going to have a one-way table. We only have one list of or not one WIS, but like one row of observations, okay? And the categorical variable, it has specific values, category 1, category 2, all the way to category K, whatever K might be. And within each of these categories, based on the data, so the observed counts that you see right here is my data. I collect the sample, how much of my data, how many observations fell into this category, how many fell into here, how many fell into here. And when you add up all the observed counts, that adds up to n, which is your sample size, right? Because every individual in your sample has to fall into these categories. So it makes sense that the observed counts must add up to n. So that's the data part, but again, we still haven't addressed, okay, well, I assume that the null that it fits a particular distribution of probabilities. So under the null, so now I'm separating the table. So this is still a one-way table, okay? But I just separated the table right here just so you could see it side by side. So under the null hypothesis, I'm saying that, oh, a certain percentage or a certain number of proportion of observations should fall into this category. Like again, if I go to the 1/4, 1/4, 1/4, 1/4, then I should expect 25% to be here, 25% to be here, 25 to be, etc. So the null statement that I'm assuming to be true, I'm just saying, oh, I know the probability distribution that goes into each of these categories, and all of those probabilities should add up to 1, right? So that's just going back to our axioms of probability. All right. So under the null, I'm assuming that I know the distribution going into each of these classes. Okay. But as you guys hopefully remember from the boxes, okay, if I have observed counts, okay, so these are just whole numbers, like 20 things fell into this category, 15 fell into here, 14 fell into there. But these are probabilities. So I can't compare observed counts with the probability. So if I have the null distribution right there, and I have observed counts, well, what am I going to do? Well, if you go back to the formula for the chi-square, I have to compare observed counts with expected counts. So the expected counts are what do the counts look like under the null hypothesis. So if I know the probabilities under the null, then I should be able to find the expected counts. So the expected counts, going back to that picture with the boxes, is just n times p, right? So n is right there, and I expect n or p1 knots of that n observation sample should fall into this category. This is my E1. I should expect P2 naught percent of the sample to fall into this category, which is E2, and then I just do this across all categories. Just take the probability of this category under the null, just multiply it by n, and then when I add up all the expected counts, it should also add up to n as well. All right? So that's why, again, I explained to you guys the multinomial model, because when you have multiple classes, how do you find the expected counts of that? Okay, it just turns out it's just n times p, but just across all of the different categories. Yes?
Would it matter if instead of comparing the counts, you divided the counts of each category by n and then compared the...
Like the probabilities?
Yeah.
That I'm not sure, actually. That I'm not sure. So so instead of doing expected counts, you just divide these by n, right? I feel like that would do some change to the chi-square value to some extent, but I don't know how that exactly would change it. But I could look into that and get you an answer. But what College Board wants you to do is to compare counts as opposed to compare the probabilities. Okay, so I don't know, maybe I'll look into it and see what that might look like, but we'll see. I'll have to investigate it myself. All right, but for right now, just assume you can only do counts. All right. So again, the whole purpose of this is that under the null hypothesis, I want to get what I expect the counts to look like under the null so that I could compare my observed counts with the expected counts in that category. And I could do that across all categories so that I could get my test statistic. All right? Again, I wish the flow was a little bit better, but once we have the expected count, so I just show you guys how we get the expected counts under the null. As I started today, we're not dealing with normal anymore. So if you guys remember from our conditions, that middle one was normality. Throw it out the window. We are not talking about normal anymore. So when we have chi-square now, we have something called the large counts condition. And the large counts condition just says that all the expected values that we computed must be greater than 5. Okay? So if you go back to the previous example didn't have any numbers, but when you compute the expected values under the null, we should check to make sure that they're all greater than 5. Okay? So that's our new condition that we have to check now. All right? Which isn't a very difficult one because we could compute expected counts on the calculator pretty quickly. So it's a very easy check. Okay? This is almost equivalent to the n times p, n times 1 minus p is greater than 10. It's almost the same as that, except we just do it across all categories. Okay? And then once you get your observed values and your expected values, as I showed or kind of showed you guys, you're going to put that in the chi-square formula, and then you get a chi-square test statistic. In your packet, you have a table, a chi-square table with your normal and your t-table. You have a chi-square table as well. And the idea here is that you want to find a p-value under the null hypothesis that you get a chi-square value that's greater than the one you observe. So for our purposes, you guys are doing right-tail tests all the time. You're not doing a two-tail test. You're not doing a left-tail test. You're doing a right-tail test because, as I mentioned before, if you have a very large chi-square value that's way over here, then that signals to us that the null distribution and the observed the observed data had large deviations, right? Because in that formula, O minus E, if the differences are very large, then the value that we're adding up in this chi-square chi-square test statistic should give us a very big value. So that means it's going to push it all the way out here, which means that if it's way out here, then we should be in the rejection region should be on this side over here. So in this case, we're only dealing with right tails. We're only looking for extremely large values of chi-square, which signals to us very big departures between the data and the null hypothesis. Okay, so again, your calculator will compute the p-value, but if your p-value is greater than alpha, as before, fail to reject the null. P-value less than alpha, reject the null. All right, so we're still doing the same decision rule based on p-values. And again, your calculator will give you the p-value as well. All right, and then just like that, we're here at the end of chi-square goodness of fit. Here's the little recipe, so there are a little bit of changes. In the first step, you don't have to identify parameters. So it's just going straight into what procedure are you doing and state the hypotheses. The conditions, notice that random sample and independence are still there, but large counts replaces normality. That's just the expected counts must be greater than 5. And then you carry out your hypothesis test. The test statistic is this guy right here, O minus E squared divided by E, and you take the sum across all classes that we have. So our chi-square random variable, if it has k classes, degrees of freedom is k minus 1. We get a p-value, and then we interpret the results exactly as before. Okay? So yeah, that's chi-square, at least the first test. Any questions? Does that make somewhat sense? I sure hope so. All right. All right. Well, again, I don't think any other stat teacher explains it like this. So either you guys are very lucky, or I don't know. But again, I imagine a lot of stat teachers are saying, "Oh yeah, this is just the formula. Just know it." All right. But hopefully, the slides illustrated why, again, this all works, okay? At least gives you guys a better understanding other than just saying, oh, there's the formula. All right, so we'll go through an example. This is actually a very classical example. We're just talking about a dice roll, all right? So this is an easy example where it should be a very intuitive process in terms of, in this example, we're just saying, hey, I roll a dice and I want to know if it's a fair dice. Okay? So, in this example, we want to do a test at the 5% level, and we want to test to say that we want to find evidence that the dice is not fair. So, under the null hypothesis right here, we are going to assume that it is fair, right? So that's what we're going to say. Now, let me ask you guys this. If I say that the dice is fair to begin with under the null hypothesis, what are the probabilities in each of these classes if it's a 6-sided dice? Just what does intuition say? 20 each, right? So, well, that's the expected counts. So, the expected counts, I should expect if there's 120 dice rolls, and if I assume under the null that the dice is fair, then I should expect equal numbers of rolls in each of these values, right? So 120 divided by 6, 20 each, but under the null, I will assume that each value will occur with equal probability, which is 1, 6, 1, 6, 1, 6 across the board. Okay, that's under the null hypothesis. If I assume that the dice is fair, I should expect that each value should occur with equal probability, 1, 6. And then when and how do I get the 20 right here? This is just n times p1, which n right here is equal to 120. That's just 120 times 1, 6. That's 20 right there. And then if you go here to 3, that's just n times p3, which is 120 times 1, 6, 20, right? And that's, of course, across the board because they're equal probability, okay? All right, so again, hopefully that makes sense. That's just common sense that if we assume that the dice is fair, then we should have equal numbers of rolls in each of those values, okay? Let's see, is everyone okay with that? That, again, this is supposed to illustrate goodness of fit, where the number of rolls that we have, if I roll a dice 120 times and I count how many values I get in each of those, or how many observations I get in each value, what I'm going to do is compare the counts that I observed against the expected counts, because I expect them to be 20 across the board. Does the data agree with that, or are there any significant departures from that, essentially? All right, so if everyone is good with this, I'm going to start the tedious process of going through this 4-step recipe again. And then if you guys want to see another example, I could do another example, but again, we'll start with this first, okay? So in this case, there's no parameters. There's no parameters to state as of yet, okay? So in this case, to test whether or not the die is fair or not, okay? Or I guess if that's redundant, okay? Just to test whether or not the dice is fair. An appropriate procedure is a chi-square, so now I have to insert this guy again. Okay, chi-square test for goodness of fit. Okay, so that's my procedure with the following hypotheses. Okay, so again, you guys know the drill. So the null hypothesis in this case, we're just gonna say, oh, assume that the die is fair, i.e. that each value should occur equally. Okay, that's what a fair dice means, right? That each value has the same probability. Okay. Under the alternative, we're gonna say that or the die is not fair, or in other words, that at least one of the values occur disproportionately. Disproportionately compared to the null. Okay? So that's what my hypotheses are like. So the dice is fair. I'm going to assume that to begin with. That's the basis of my expected values, 20, 20, 20 across the board. Now I'm going to try to find evidence, the data that I collected to say that the dice is not fair. Okay? Yes? Sure. All right. Now, some of you guys might prefer to write your null hypothesis like this. I'm just going to make a small digression if I can. Okay? So, it's also acceptable to write your null hypothesis like this, and I'll highlight it in yellow just so that we are clear that this is just an optional way to write it. Okay, so you could also write like, oh, P1 is equal to P2 is equal to ... equals to P6, which are all equal to 1/6 probability. You can write your null hypothesis like this if you would prefer, but that means, but looking at how you stated this null hypothesis, you introduce variables that are, who knows what P1, P2, P6 are, right? So in that case, you do have to go back to the beginning and say, let's, P1, P2, so you have to define them. So it's up to you. Either way is acceptable, but just make sure that you guys are being, covering your bases. So we can say let P1, P2, all the way to P6 be the probability that a 1, 2, ... 6 are rolled, respectively. Okay, so P1 is the probability that a 1 is rolled. P2 is the probability that a 2 is rolled. Blah blah blah. So if you define what these are from the beginning, then you can state your null hypothesis as P1 is equal to P2. So just know that the part that I'm highlighting in yellow is optional, but if you decide to write it like this, make sure that you guys define your variables. Okay. Is this okay for now? All right. So 2, the condition, so SRS, we have a dice, so unless there's some bias in selecting a certain dice, I think if you just pick a dice, it's randomly selected, so assume that the die was randomly selected. Okay, I mean, there is no sampling in this case. Okay, the next one is large counts. So again, notice that is not normality. So because we computed the expected values, they're right there. So because all expected counts are equal to 20 and therefore greater than 5, the sampling distribution of dice roll counts follows an approximate normal distribution, or sorry, chi-square distribution, not normal. With 5 degrees of freedom. Okay? So that's the large counts. And just so you guys are aware, you do, on the AP test, if you're given a chi-square problem like this, you do have to state what the expected counts are. You can't just say, oh yeah, trust me, I checked the expected counts. You do have to write like a table to say like, oh, these are the expected counts, so that they can verify that, yeah, they're all greater than 5. So just as a note, normally you must record all expected counts here to show this condition. Okay, but because I have it right there, I'm good. Okay, but normally when you have to actually compute the expected counts by hand, you do have to create, I guess, separate table and just say expected counts in this category, and show them physically that, yeah, they are greater than 5. Yeah.
What does DF mean?
Degrees of freedom.
Oh.
Okay. So again, I already have them there, so I tried not doing that. Okay. Independence. Well, each observation is the result of a random process, right? Assuming under the null, so let's say under the null, okay, each die or each value of the die occurs with equal probability. Therefore, each observed roll is independent of the next, right? So a dice roll once, you roll it again under the null. If they're all equally likely, then guess what? We have independence. That's just strictly from a probability sense. Okay? Now, normally I would have to do the sampling without replacement business, but I don't have to do that because once I pick a value, like I roll the dice and it's a 5, well, the next one could be a 5 as well. So there is no sampling without replacements. So if there is no sampling without replacement, I don't need to check the 10% rule. We're good. We're done with independence. Okay? And that's my condition. Those are my conditions right there. Step 3 is my calculation. So going to the calculation part, my chi-square random variable, I said that it has 5 degrees of freedom. The reason for that is because if you look at how many classes I have, k is equal to 6. So therefore, if I have 6 classes, I take 1 less than that, and that's my degrees of freedom. So I have 5 degrees of freedom. This is going to be the sum of I going from 1 to 6 of OI, or of the observed values, minus the expected values, or counts, squared, divided by the expected counts. Okay? Now, for these problems, I would just write out a few of these. You do not have to write all 6 of them. So this is what I would suggest doing. So if we look at the very first class, the ones, I'm going to write that as the observed counts, which is 18. I observed 18 ones. Subtract its expected counts, which is 20. Square that, divide by 20. That's the first class. going to the second class, right here, I'm going to say plus 24, that's the observed number in the second class, minus 20 squared divided by 20. Okay, and then once you have it started, I would just recommend just skip to the end. So just do the dot dot dot. So plus dot 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 plus the last one, which is observed 22 sixes minus the expected 20 squared divided by 20. That's what I would do. Okay, so that we show your work. You do not, I would not just waste time writing out all of them. Okay, because that's just time consuming. So I would not write all of them. I would just start the formula with a few or a couple and then just do dot dot dot. I think that if you could plug in a couple of them correctly, I think we could assume that you could plug in the rest correctly. Okay. Now let me show you how to do this on a calculator, and then we can get closer to finishing this. All right. So calculators. You guys see that? Okay. So with this one, you're gonna have to put the data in the list. So hopefully you guys remember how to do that. Press stat. The very first one is edits, and then you're gonna have to maybe clear some lists. That's fine. But sorry, you guys don't have the observed counts. I guess just copy it off my calculator. 18, 24, 16, 19, 21, 22. Okay, so those are the observed counts. Okay, and then in the other list, you have to put the expected counts. Okay, so this is one way in which we can do this. You can't just put 20, 20, 20. You can do that. Another way, because in some problems, they're not going to be equally likely. So what you can do is you could just put the probabilities in here. So typically under the null, you're going to have, the class 1 will have this probability and class 2 will have this probability. So I recommend putting the probabilities there first. So once you guys have that, and then once you have all the probabilities, 1, 6, 1, 6, 1, 6, I would highlight list 2 and then just type, because when you start typing, it's going to go into here. I would take all the probabilities in list 2 and multiply it by n, which is 120. Which gives me, once you press enter, it'll give you the 20s right there. The reason why I want to show you guys that, because what happens in a problem if your probabilities are not the same? What if you have class 1 is 50%, the second class is 30%, the other ones are 10 and 10, right? So this is an easy example where all the probabilities are the same, but what happens when you get a problem where the probabilities are not the same? So that's one way in order to do that instead of computing them individually one at a time. Okay? Are we good so far? Okay, I hope so. All right, so now that we have the observed and expected in the list, we're going to go to item D on the list, which is near the bottom. That's chi-square goodness of fit test. We will get to item C, chi-square test, on Monday. But chi-square goodness of fit test, you're going to press enter, and then it's going to ask you, where are your observed values and where are your expected values? Yeah, Miles?
The goodness of fit test is on my calculator.
It's not?
Yeah, mine's a TI-83 plus.
Try that then and see what you get, all right? Just try chi-square, all right? So I have my observed and my expected. My degrees of freedom, I guess you have to put this in manually. I have 5 degrees of freedom, okay? So once I put that in, I press calculate. My chi-square test statistic, if I were to add up all 6 of those values, is going to be equal to 2.1. The p-value is 0.8351. So it's a very large p-value, okay? So that's how you operate the calculator. Let me write that down myself. And then it's pretty easy once you put in the values. And pretty much for all problems like this, you have to be given a table of values. So this is the data entry part. Like if you saw this on the AP test, yes, you're gonna have to probably do this. Okay. 8351. All right. Miles, did you get the same thing? You
No,
did?
it don't allow me. It won't allow me to input this.
Okay, I'll have to look at that with you once we're done. All right. So give me a moment to finish this. All right. So if I were to add up all of these, if I were to write out all 6 of them and add them together, it would give me 2.10. That's the value of my test statistic. My p-value was 0.8351. So comparing that against alpha, this is greater than my 5% level of significance. Therefore, I should fail to reject. Okay, so going to step 4. Okay, because again, it's the same script. Because the p-value of 0.8351 is greater than the 5% level of significance, there is not convincing statistical evidence that suggests that the die is not fair. So again, I know it's kind of confusing that it's not, but we are saying that in the end that the dice is fair, right? Because we failed to reject the null hypothesis. So I know English double negative is not the easiest to understand, but this is how we would write. So we did not find evidence that the dice is not fair, meaning that we have evidence to say that the dice is fair. Okay, so again, confusing, I know, but that's just how it is, right? And then there's the problem right there. Again, it's not any more work than what we've done so far. It's just different because we're talking about different test statistic and distribution. Okay, so now we're just saying that the observed values right there, the 18, 24, and 16, 19. That's not too different from the 20, 20, 20, 20, 20, whatever, to say that, it's unfair. So we have to say that the deviations are not so big that we can't just reject the null hypothesis. So we're saying that it's close enough to what is expected that we can't reject the null. Yeah.
So to figure out if we're using a chi-square test, like it would be a theoretical probability versus like an observed, whereas like a 2-sample thing would just be 2 samples and you're finding the difference, right?
Right. Yeah. So that one we're trying to test that the difference between 2 populations is, like 0 or whatever. But for this one, we're just saying like, hey, the population has a particular distribution. Does that fit the distribution we're assuming it to be?
So technically it's like a 1-sample thing, right?
I mean, this is a 1 sample. Well, yeah, technically this is a 1 sample. The data is coming from 1 sample, yes. But we are comparing our 1 sample, our observed roles against a null hypothesis, right? So that's kind of like the ambulance question is kind of similar to that one, okay? So I know we had talked about that. All right. How did this example treat you guys? Is it pretty reasonable, logical-ish? Okay. So we don't have that much time, so I'm not going to go over this example unless you guys want me to go over like a very specific part. But notice that in this example, this one is talking about the distribution of car colors in North America. But we grab a sample of car colors, 300 of them, from a city. And we're going to say, does the distribution of car colors that describes the population of North America, does it fit the city distribution of car colors? So this is very different than just dice rolls. But notice also that there are more classes. You can have a white car, black car, gray car, red, etc. So you have more classes. But notice that each class doesn't have the same probability too. So in this case, it's not going to be, what is there, 7 of them? 1, 2, 3, 4, 5, 6, 7. It's not going to be 1/7, 1/7, 1/7, 1/7. This is what we're hypothesizing it to be. This is what it looks like in all of North America. And we want to see that gathering a sample from just this one city, does the city's distribution of card colors, does it fit the nation's distribution of card colors? So notice that, again, these, you're not always going to get equal probabilities like the one we had just a moment ago. Okay? Is that good enough for chi-squared? Do you guys feel okay about it?
Yeah.
Okay. Again, hopefully that makes sense. I mean, hopefully treated you well after just knowing chi-square in less than 2 hours. 2 hours ago some of you guys didn't know what chi-square was. So hopefully that made some sense. All right. But in any case, that is the problem. It's very much the same thing that we've been doing, but just looks a little different. All right. So your homework, you will have homework on this because on Monday I am going to do the other 2 chi-square tests. So you do have homework on goodness of fit. I will publish that by, after school. Okay, so I forgot to do it for first block. So I will have it ready for you guys by the end of today. All right, so just be aware there is homework. It is due on Monday because on Monday we're going to do chi-square tests for independence and chi-square tests for homogeneity as well. All right, so that's it for today. 5 minutes. You guys have it to yourself. Homework will be